How did we do on the homework here? 20? Okay, good. So what I want to talk about. So here's what I want to think about this one. So we want to think about this one by expanding the knowledge or the meaning of these symbols, right? So we know what -4 is, obviously. Do I have? I don't. Okay. I lost my pen. Come on. Interesting. Is it open? Is it? Oh, it is open. Must be on the wrong. There we go. Okay. Okay, so you know what -4 is? So what is n factorial? So when you look at n factorial, you have to have an image of what that's what mathematical thing that's telling us, right? So n factorial means what? N times, right? Okay, so when you look at n factorial, you see that and you think this. You think this all the way to 3, 2, 1. Okay, so it's just going to keep multiplying, starting at the value of n, just keep multiplying down by whole numbers until you get to 1. Okay, and then what about -8 to the n? So when you see -8 to the n, you have to have an image of what exactly that is. Okay, 8 times 8? Yeah, so we're going to take -8 and we're going to do what with it? Multiply it by itself n times. So something like this, and then we note that there are what? N -8s. So look at what happens. How many factors are there in n factorial? How many factors does n factorial have? Or how many? Yeah, it has a lot more than n, but there are n things multiplied together. And what about -8? How many things multiplied together? N. So look, we can group these. We can, for every one of these things multiplied up top, we can group it with one down here, right? So -1/8, 2 over -8, 3 over -8, and then all the way up to net n over -8, n minus 1 over -8, n minus 2 over -8. So the first 8 terms, right, will be less than or equal to 1, right? All these will be fractions. When you get 1 times 2 times 3 times 4 up to 8, 8 over -8 will be -1, but all those will have a magnitude less than 1, right? But then what about when n is greater than 8? All of these will be what? Yeah, so less than -8, right? So bigger negative values than -8, or so than -1, sorry. Right? So we get to 9 over -8, 10 over -8, 11 over -8, okay? And so what happens when you keep multiplying by a larger and larger number greater than 1, and then you let those numbers continue to get larger and larger? Yeah, definitely going to diverge, right? It's definitely going to diverge. And then, so then the question is, so this is going to get very, very large. But then, so whenever n is even, it looks like this will be positive. Whenever n is odd, this will all be negative, right? And so, but then we're multiplying by -4. So does it get exclusively large negative? Does it get exclusively large positive? Or does it split up? Yeah, I think this is going to split up, right? Because this is going to alternate, right? This is going to alternate. So it's not going to just head to -infinity or head to +infinity, but it's going to split up. So I think State your answer as divergent. div. So this is it's gonna alternate between larger and larger positive and negative numbers as n gets larger. Okay. Okay. So did the reasoning make sense?
What if we had a positive denominator?
Okay, so if you had a positive denominator and then you had this -4, then all of your terms are getting larger or what? Negative, right? If you have positive, all these fractions or all these ratios are positive, and you're always multiplying by -4. So this big fraction will get larger and larger positive times -4. The whole thing will get larger and larger negative. Minus infinity, yeah. Yeah.
So if we were doing this on like a test, would we have to write it out and show that?
Yeah, you have to have some kind of reasoning, right? So the point of these convergence, divergence of sequences, you have to justify your answer. And we saw there's different ways. So here, this way, I'm just noticing that I can make a ratio out of all these terms, all these factors. And then once n eclipses 8, then these factors just keep getting larger and larger, greater than 1. So this thing is going to get big. Yeah. So yeah, you're going to have reasoning for your answers for convergent or divergent. Other questions? Okay. So today we're going to talk. So we've kind of talked about series, and then maybe if you want to, in recitation next week, we can talk about a few of those sequences on the written homework, if you want to go over those in recitation on Monday and Wednesday. So we're going to change from sequences to series. Okay, so what did we say? A sequence is an ordered list. Ordered list. That's what we've been working on. All these things you've been working on was making a list and looking at that sequence in that list to see if it's converging on a number or not. So convergent or not. Okay?
Mark, are you recording?
I think so. Yeah, thanks. Okay, and so then what is a series? A series is when you take all the numbers in the list and you add them up. You sum them up. Okay? We never want to lose. So things will start getting really involved, algebraic, confusing sometimes. We never want to lose sight of this. The basics can always or can often get us out of a jam if we remember what we're looking at. Okay? So a sequence AN and the associated series is this. This is what this means. Again, I should have braces around this. So given a sequence AN, we know that the first number in the list is A1, the second number in the list is A2, etc. So the series then is adding them all together. Adding them all together. And we've seen, so to kind of make that more efficient, we have a symbol for that, right? What's our symbol for that? We've seen it. Sigma, right? Sigma. So we're going to use sigma to help us here. And so really we're saying the sum of all the terms of the sequence. So it's going to be sigma AN. All right? And so then the bottom tells you the first value, n equals 1. And then this tells you the last value. So if this was n equals 7, if this was 7 up here, you'd be adding 7 things together, right? A1, A2, A3, A4, up to A7. If it's infinite like this, then the sum never ends, right? It just keeps adding on terms from the sequence. So this is huge, right? So whenever you see this notation right here, you think this, right? You have the right image of what's going on. Whenever you see summation notation, you think, oh, it's the sum of all the terms of the sequence. And then that just, the sigma isn't so scary anymore, right? It's just telling us that we're adding a bunch of things together and they're all similar, right? They change from one to the next, but they all kind of have a common formula to them. Okay, so let's look at, we talked about this sequence, and this sequence was of the odd number, so what would that series look like? So then we could write that this is the sum of 2n minus 1. And so can you write out what that means, right? We'll do this a lot. When you see that, you think what? Write out literally what it means. Go. And so let me just say, it means, so you let n equals 1, and you get the first term of the sequence. And then you let n equals 2, and you get the second term of the sequence. And then n equals 3, and you get the third term. And then now it's indicating to add them all up, okay? All right, Natalie. Is she here? How'd it go? Tell me.
So we would get like 1
Uh-huh.
plus 3 plus 5.
Good.
Plus all the way to
That's it. Yeah. This is what you should have written. That's what you should have written. 1 plus 3 plus 5, etc. That's exactly what this means. Okay? And then we talk about whether, just like sequences, we talk about series, whether they're convergent or divergent. If they're a convergent series means it adds up to a number. It adds up to a number. Okay? Divergent means it just, it never adds up to a particular number. It could oscillate, the sum could oscillate, or it could get really big, positive or negative. So this one, convergent or divergent? Clearly. This is just going to keep getting bigger and bigger by bigger amounts, right? So we say this, okay, and so the way we're going to think about convergence or divergence is we're actually going to take this sum and we're going to make another sequence out of it. And it's called the sequence of partial sums. So we kind of go in a circle, right? The series itself was based on a sequence of numbers. And so the series then is the sum of those numbers. But then what we do is we think about a new sequence of partial sums. And so this is S1. And then S2 is adding the first two together. And then S3 is adding the first three together. So this would be S3. S4 would add the first term. So what is the sequence of partial sums? It would be 1. What would be the next? What would be the second partial sum? 4. Then 9. Then 12, right? Then?
You accidentally wrote 5.
What does that mean to write? That's why you're confused. 9?
Yeah, 9.
So 4, 9, I wonder you got quiet. 16, then 25, right? So whatever the sequence of partial sums does, that's what the series does. Because you keep adding another term. So you're looking at what happens if you keep adding more and more terms. So you're looking at a sequence that tells you what happens when you keep adding more and more terms to what you had before. So clearly, that sequence, this is Sn, right? Sn is divergent. These numbers just keep bigger and bigger. So therefore, the series is divergent. So whatever the sequence of partial sums does is the same as the same conclusion as what the series does, what the series equals. Does it make sense? So make sure you got those sequences straight, right? There's the original sequence, that we just take the terms and we add them up. Then out of that sum, we create a new sequence of terms where we keep each next term of the sequence is adding one more term of the series. Adding one more from the series. Okay, so let's look at another one. How about this? 1 over 2 to the n. Okay, so I want you to write out, so we know that's the sum as n equals 1 to infinity, 1 over 2 to the n. So go ahead and write out, when you see that, what does it mean? What do you think? Gerardo, back there. Did you get it?
Yeah.
Tell me.
0.5 plus 0.25 plus 0.125.
Okay. All right. So, yep. 1/2 plus 1/4 plus 1/8. This is what you should have. 1/16, 1/32. Okay. So now to analyze this, we're going to look at the sequence of partial sums, but we'll think about it as the turtle that's walking across your backyard, right? You guys don't have a turtle walking across your backyard?
Yes.
Of course you do. We all do. Okay. So,
I got this from going Western Rock.
all right. So, what is the first term of the sequence of partial sums? 1/2. So what happens? Your turtle walks 1/2 way across your lawn. There he is. All right. S1 equals 1/2. What is S2? S2 is the second partial sum. 3/4, right? So when he walks the next 1/4, now he's made it a total of 3/4 of the way across. So S2 is 3/4. Do you see it?
Oh, yeah.
What is S3? 3/4 plus 1/8, which is 7/8. S3 is 7/8. There's the turtle, 7/8 of the way across your backyard. That's S3. S4 is 15/16. So take 7/8, you add 16. So this was S3. This is S4.
31/46.
So 15 over 16th, and then S5 would be 31 over 32. And so now we imagine this sequence, right? This sequence, 1/2, 3/4, 7/8, 15/16, 31/32. So, does the sequence converge? Does the turtle make it across the lawn?
Infinitely close. Converges that.
Yeah, but remember that we're looking at what? The limit as n.
Versus 1.
Does this limit exist? Yes, the limit of Bn is. So if you add up all infinitely many terms of this, he makes it. It's 1, right? It's equal to 1. He gets there. So as n gets very, very, very large, turtle walks 1 lawn length. 1. The sum of those is 1. So this geometric series equals 1. But you got to add all infinitely many terms together to get 1. If you do any partial sum, it will be a little bit less than 1. But if you add all infinitely many terms, it's 1. Can you buy that? Wrap your head around that? Okay, cool. So this is a convergent series. The series of partial sums, the sequence of partial sums converges to 1. Therefore, the series equals 1. And the turtle makes it all the way across. Okay, so let's look at, here's a sequence. So let's analyze this as a sequence first, okay? So yeah, you guys are experts now. We've got a couple days. Analyze this as a sequence. So maybe let's write out the first several terms, and then let's analyze it for convergence or divergence. Go, everyone do it. Write out the first 3 or 4 terms, so we know what we're talking about.
Are we validating it as a series or?
No, as a sequence. Sequence. Is Ralph still in the class? Ralph Kissel? Is it here? Or is it? That's all right, I'll just call him. Okay, where's Ralph? Ralph. How'd just writing out the terms of the sequence go?
5/8, then 20/11.
Okay,
45/16. 90/23.
that's good. Okay, and it's going to keep going on like this. And now we look at this and we apply our techniques and we say, is this convergent or divergent and why? Alec Warren, did you come up with that?
Yeah, it's going to converge to 5.
It's going to converge to 5 is what he says. What do you guys think? And how did you reason that?
So you looked at the equation, the coefficients
Uh-huh.
to the numbers with the greatest exponents, 5n squared over n squared, with the coefficients to the variable of n being 5/1.
Okay, so we got the same degree in the numerator and denominator. So we know that if we thought of the function 5x squared over x squared plus 7, and we took that limit, the limit of that function would be 5, right? And so therefore the limit of the sequence is also 5. So let's think about this sequence then. So let's suppose we get out to the millionth or the billionth or the trillionth term. What will the sequence be like when we get out to very, very, very large values of n? So what will the sequence be like? What will this number be like? What's that?
So very close.
Essentially 5. So let's put 5 in parentheses, and it means incredibly close to 5. All right, what about the next number?
Even closer.
Even closer to 5, right? And we were already incredibly close, and it's going to be even closer. So what's going to happen for the rest of, so here we are at the trillionth term, trillion in the first, trillion in the second, and then it's going to keep going. And what's going to happen as it keeps going? We're essentially just going to have 5s repeating forever, right? 5s repeating forever.
How do we
Okay.
define when we get there?
What's that?
How do we define like the point at which we can just assume something is essentially 5?
Depends on computational
Yeah, so,
technology.
I mean, one person says 5 decimal places, another person says 10 decimal places, another person says
Just
20
arbitrary.
decimal. Yeah, it's just like, we just are saying when n gets really, really, really big, these numbers are going to be so, so close to 5, they're like indistinguishable from 5, right? So we end up just getting 5s Okay, so now let's think about the series. And now that we've fully understood that sequence, thinking about the series should be instantaneously easy. What's going to happen to this series? What's going to happen if we try to add up all the terms of the sequence? If you're not thinking divergent, you're not awake, right? Okay? You're just going to end up just adding basically 5 forever. Okay? I thought it was a great result too. Okay, so this diverges, right? Diverges. So this really begs the question, if we have an infinite number of things that we're adding together, won't it always just get really, really big? You just keep adding on. So what if we want to get a sum of infinitely many things to actually add up to something? What has to happen with a sequence? Smaller to... Doesn't that sequence absolutely have to converge to 0 in order for us to talk about having a finite sum? What if it converges to 0.001? Then you're just going to keep adding 0.001, and you'll never run out of 0.001s to add up. So that will still diverge. Yeah, John?
If you have like a cyclical sequence, will it kind of diverge or converge to 0? If you add like a 1, negative 1.
So think of the series, think of the sequence of partial sums in that case.
Okay.
What will the sequence of partial sums do in that case then? Will it hone in on a particular number, or will it jump? It'll keep jumping. And we've seen that case, right? So whenever a sequence is jumping between different numbers, divergent. It's got the sequence has to, in this case, the sequence of partial sums has to hone in on one number, and that's the only way it converges. So if you have if it's jumping, so if it's like 5, negative 5, 5, negative 5, 5, negative 5, then what's your series sequence of partial sums is what? 0, 5, 0, 5, 0, 5. Divergent.
Why
Ben?
is that 1, negative 1 thing? Why is it simplified as a 1/2?
It's a special sum. Don't think about it for this class. Like that summation symbol means something else. The Ramanujan sum.
Oh, okay. Yeah. Okay, so this brings up what's called the divergence theorem. And so this is the first really important thing about series, because it has to do with giving a series a chance to converge, right? So here, we'll state it and then we'll talk about it. So the divergence theorem says, given a series, if the limit of the sequence does not equal 0, or the limit does not exist, then the sum can't add up to a single value. So what are we saying? The sequence must converge to 0 in order for the sum to be finite.
In that situation, would the series always be equal to 1?
No, you can have series adding up to all different values.
Okay.
In what situation?
When the limit is equal to 0, would the series then?
It can add up to any number. You have all kinds of sequences. It can give you all kinds of sums of different numbers. Yeah.
When you have the brackets around the A sub n, does that always imply a
Sequence, right? So the braces, right? The braces always means sequence. Okay, so this should make sense based on our last example. If your limit of your sequence heads to something other than 0, then what happens for large n? You just keep getting essentially that number over and over and over again. And if you try to add that up, it's going to be infinitely large. Okay, questions on the divergence theorem?
Does the condition that you've written out imply that if the sequence goes to 0, that the sum will always be finite?
Okay, we're getting there. Don't get ahead of me, please. Okay.
Get a lot of questions.
Other questions? Okay, so let's look at geometric series. Geometric series. So we saw, what was a geometric sequence? What was a geometric sequence? R to the n, right? So likewise our geometric series, and we can also throw a coefficient on there. So n equals 1, a r to the n minus 1. A r to the n minus 1. Okay, so you see that? So a is a constant, it's like a coefficient. R is also a constant. Okay, it's some number. So a and r are just some numbers, a and r. And then we're going to do a r to the n minus 1. That's going to be our sequence, and we're going to add all those up. So when you see that, you think what? Can you write out what this thing is equal to? Caitlin, did you get it?
No, not yet.
What would the first, the first term, what would be the first term? So what's the first value of n? First value of n is 1. So when n is 1, what do you get for this, Caitlin? When n is 1?
Put it turn to 0, because it's r.
R to the 0.
So just 1.
And times a, right? So the first when n is 1, you get a. And then when n is 2, you get ar to the first, or ar. Then ar squared, etc. So this is when you see a geometric series, this is what it's like. There may be some coefficient a, and then what? Every term is multiplied, that you add is multiplied by one more r than the previous one. It's just like our geometric series. Just like our geometric series. Geometric sequence, right? Geometric sequence. Okay, and when did the geometric sequence converge? The sequence itself? So say a r to the n. We said that converged to 0 when? Hopefully you remember that's between -1 and 1. Okay? That's when the sequence converges. So what about the series? What about the series? For what values of r, then when we add them all up, do we get a finite value? Okay, so we know that we get the sequence goes to 0. Okay? Does that mean that whenever r is between -1 and 1 and the sequence goes to 0, does that mean that the series is finite? The sum is finite. So let's take a look at that. So we want to look for what values r does the geometric series converge? Okay? So what we're going to do is we're going to look at the sequence of partial sums, right? Sn. So can you write out Okay. All right, so the nth, so what we want, don't write out the sequence. What we want is the nth partial sum, right? The nth partial sum. So write that out. What's the nth partial sum? It's going to be the first n added together, right? So I'm not saying the sequence, I'm saying the nth term of the sequence of partial sums. So what is the nth term? Or what do we add up to? AR to the n minus 1. And we stop, okay? Because this is a partial sum, right? This is a partial sum. It's just the first n terms added together. Okay, then what we're going to do is we're going to multiply this by r, multiply both sides by r. And you say, why do we do that? And I say, because it works. Because it works, okay? So now when I do that, I'm going to get everything times r, but I'm going to shift it over so we see how things line up. So a times r is ar. So it's going to get the same thing, but I'm going to start now with ar, and end with ar to the n, right? So I'm going to have ar to the n minus 1, but then I'm going to have one more term. And what we're going to do is we're going to subtract. And lots of things are going to go away, right? So all those, I lined them up so we could see that when we subtract, all those terms in the middle are going to be 0. So we're going to get the nth term of this sequence of partial sums minus r times Sn equals, when we subtract, we can get a, all these are going to go away, right? 0, 0, 0, and then plus ar to the n minus ar to the n. Do you see what happened? I subtracted the second. On the left, I subtracted the second from the first, and on the right, the second from the first. Okay? And so we know whatever the sequence of partial sums does, the series is going to do. So we're going to isolate the Sn. And let's isolate a here, so we get a times. Nothing's hard about this, right? There's nothing that's hard. I just wrote out the nth term of the sequence of partial sums, multiplied it by r, subtracted, and now I just factored out s sub n on the left, I factored out a on the right. And so then what is Sn is a times 1 minus r to the n over 1 minus r. And so now, then as n gets big, we really just have to focus on this r to the n, right? So if r is outside the range of -1 to 1, this will blow up, right? So this whole thing will blow up. But if r is between -1 and 1, then Sn equals, what does that go to, right? Sn gets really, really big, and r is between -1 and 1, then that becomes 0. So we're left with a over 1 minus r when r is what? We need that to go to 0, right? And when does it go to 0? -1 to 1, like we said before. So when the sequence converges to 0, right? We get the same condition. When the sequence converges to 0, when r is between -1 and 1, this sum will be finite. And even better, we know exactly what the sum will be. A over 1 minus r. That's really nice, right? If r is outside of those, then your sum is going to diverge, right? Because by the divergence theorem, if the sequence diverges, which it does for r outside this range, then the sum diverges, right? Okay. Questions on that little proof of the sum of a geometric series and when it converges? Okay, so remember the turtle. What was the series for the turtle? N equals 1 to infinity of? Do you recognize what we have there? What do we have if it's 1 over 2 to the n? Look, so here's the key. When you see n in the exponent like that, you should think geometric series. That's the point. That when your n, your index, is in the exponent, you're thinking, oh, this is probably a geometric series. Can we make that look like that? How would we start? So we need something to the n. What is to the n? 1/2. But notice, n equals 1, we're starting with n, so it's not quite right. When n equals 1, we need to start with n minus 1. So how can I have this be 1/2 n minus 1? So think about, what does 1/2 to the n mean? We talked about it earlier. What does 1/2 to the n mean? What's your image of that?
Times itself n times.
Okay, and what is 1/2 to the n minus 1?
1/2 to the n
Starting
times
with
minus.
So
you would
how would you compare this number to this number?
just
But all I'm asking is, how would you compare these two? Not make them equal. How would you compare these two?
Smaller.
You have 1 less 1/2 being multiplied than in n minus 1.
Exactly. So here I have n of them multiplied together. Here I have 1 less. But I need it to be 1/2 to the n. So what do I need?
Multiply by 1.
1 more 1/2. 1 more 1/2 will give me n 1/2s. Do you see it? So I still have n 1/2s multiplied together, just written in a different form. In this form. So A is 1/2. R is. Will this series converge? Because R is between -1 and 1, so it will converge. And what will it converge to? So this will equal, what do we find? A over 1 minus R, which is,
2a.
get your smartphone sound effect ready, 1/2 over 1 minus 1/2, which is,
So 1.
and how far did the turtle, what fraction of the lawn did the turtle make it across? He made it to the wall, right? There's the 1 again. It's the same series. Now that we see it as a geometric series, we can apply what we proved about geometric series, that they equal A over 1 minus R when R is between -1 and 1. We apply it, we get 1. Did you catch it? Does that make sense? All right, so let's do one more geometric series. So the key with geometric series then is getting it into this form. So like you'll see that it's kind of, you can see that it's a geometric series, but it won't be in this form. Once you can get it in this form, then you can immediately conclude divergent or convergent based on R. And then if it is convergent, you can just crank out what the sum will be. Okay? Oh. So here we go. So what's our goal? We're trying to get this in the form of, I'll write it. N minus 1. So So we need some algebra prowess here. We need to be good at our algebra and good at our exponents to massage this so that it looks like AR to the n minus 1. Okay, so what do I want to do first? In the numerator, I'm going to do -3 times -3 to the okay, and so can I get AR to the n minus 1? What would A be? We can put the -3 and 5 together. That's our A. And then can we get something to the n minus 1? -3/4. Okay, so right now that we have AR to the n minus 1, we can say convergent or divergent series. Convergent or divergent. You should be thinking convergent because our R value is between -1 and 1. Therefore, the sum equals -3/5 over 1 minus -3/4, whatever that is. That's the sum of this. When you add all infinitely many terms together, you get that number. When you look at the sequence of partial sums, it will converge to this number. Okay? So if you looked at the first term, then the first 2 terms added together, then the first 3 terms added together, then the first 4 terms, that's the sequence of partial sums. That sequence will converge to this same sum. For those who don't like that, right? What is that? 7/4, -12 35ths. Okay, notice these terms will alternate positive and negative. So you're going to add a little bit and subtract a little bit, then add a little bit and subtract a little bit. But because those numbers are getting smaller, they're always 3/4 of the one before. That sum that is gonna hone in on -12 35ths, even though that the sequence is alternating. Okay.